Everyone is welcome to my channel. Today we are going to solve a problem which is z minus I over z minus 1 is a purely imaginary number. Here we have to find out the value of the function, that is expression modulus z minus 2 plus 2i, where z is the complex number, where z equal to x plus iy. xy belongs to the set of real numbers and I is also an imaginary number whose value is root over of minus 1. Here z minus I over z minus 1 is a purely imaginary number. We have to find out the maximum value of the function, that is expression modulus z minus 2 plus 2i, where z is a complex number which is equal to x plus iy and xy belongs to the set of real numbers. I is an imaginary number whose value is root over of minus 1. Now let us start. Here z minus I over z minus 1 equal to x plus iy minus I over x plus iy minus 1, where z is a complex number which is equal to x plus iy. Here xy belongs to the set of real numbers. I equal to root over of minus 1. This is where z minus I over z minus 1 equal to this. Here we can make the denominator a real number, that is we can convert the denominator into a real number if we multiply both numerator and denominator by the complex conjugate of the denominator. If we multiply both numerator and denominator by complex conjugate of the denominator, we are able to convert the denominator into a real number. This denominator will be converted into a real number if we multiply both numerator and denominator by the complex conjugate of the denominator. And complex conjugate of the denominator, here also x plus y minus 1 into I over x minus 1 over x minus 1 plus iy. Here this is the denominator, its complex conjugate is x minus 1 minus iy, and if we multiply the complex conjugate of the denominator, if we multiply both numerator and denominator by the complex conjugate of the denominator, this complex conjugate of this denominator is x minus 1 minus iy, and also we multiply both numerator and denominator by x minus 1 minus iy, x minus 1 minus iy. This is the complex conjugate of the denominator. We multiply both numerator and denominator by this complex conjugate to convert the denominator into a real number. So we have x minus x1, x into x minus 1 plus y into y minus 1 over, if we multiply this by this, we get x minus 1 whole square plus y square, and next part is I into x minus 1 y minus 1 minus xy over x minus 1 square plus y square. This is the complex number. It is also a complex number. It is complex value of this expression z minus I over z minus 1 is a complex number. This is a complex number whose real part is this and imaginary part is this. Now here we are given z minus I over z minus 1 is a purely imaginary number, So if we if it is a purely imaginary number, then also its real part vanishes, as z minus I over z minus 1 is purely imaginary number. Its real part vanishes, that is real part of z minus I over z minus 1 real part equal to 0. Here real part is this, so x into x minus 1 plus y into y minus 1 over this equal to 0, because this is the real part of this complex number, as this complex number is given as a purely imaginary number. So also obviously its real part vanishes, that is its real part is 0. So here we write real part equal to 0. We have written real part of this expression of this complex number is 0. So we have x into x minus 1, this is, so x square plus y square minus x minus y equal to 0. So this is an equation whose left hand side is a function of two variables, function of double variables. Double variables are x and y. So we can consider this function as phi xy equal to x square plus, this is a function of several variables, that is double variables. Here double variables are x and y. This is phi xy. Now our objective function can be considered as psi equal to, objective function is this, we have to maximize these functions, this function under the condition z minus 1 over z minus 1 is a purely imaginary number. So this is our objective function. Our aim to maximize this objective function, that is this expression. So this is objective function, which is z minus 2 plus 2i equal to x plus iy, z equal to x plus iy minus 2 minus 2i, which is also x minus 2 plus I y minus 2. This is equal to root over of x minus 2 whole square plus y minus 2 whole square. As this is modulus, so it is non-negative. So it is always greater equal to 0. It is always greater equal to 0. And it is non-zero quantity. Any modulus of any function or any expression always a non-zero quantity. So a non-negative quantity. So this is greater equal to 0. This is greater equal to, this must be greater equal to 0, because this is the value of the modulus. Modulus is always non-negative. So this is greater equal to 0. Here also this is a function. This function is of double variables. This is a function of double variable. Here double variables are also x and y. Double variables are also x and y. So this function also the function of double variables. A double variable is xy. So we can consider the objective function as psi xy. Psi xy is this. This is greater or equal to 0. Now we have to maximize this objective function psi xy. There are so many methods to maximize a function of several variables. Here there are so many methods, so many ways to maximize a function of several variables. Here we shall use the more suitable method, which is method of Lagrange multiplier. We can use the more suitable method for maximizing a function of double variables. We can use methods of Lagrange multiplier. This is the easiest way to maximize a function of several variables if we use the method of Lagrange multiplier. So here we also use the method of Lagrange multiplier to maximize this function. We have constructed the function fxy, capital Fxy equal to psi square xy plus lambda phi xy. Here phi xy is the constant function, psi square xy is the objective function. If we maximize psi square xy, we can also maximize psi xy. Our main objective function is psi xy. We have taken the maximization of psi square xy for the sake of the maximization of psi xy. So here this is the function fxy equal to this, where also lambda is the multiplier, that is Lagrange multiplier. Lambda is the Lagrange multiplier. So for stationary value, stationary value psi square d psi square xy equal to 0, because psi square is our objective function. So at stationary value d psi square xy equal to 0, that is differentiation of psi square xy equal to 0. And also phi xy is always 0, d phi xy, that is d phi xy is always 0, because phi xy equal to x square plus y square minus x minus y equal to 0, because phi xy equal to 0, so its derivative is also 0, differentiation is also 0. So we have for stationary value we have df xy equal to d phi square d psi square d psi square xy plus lambda d phi xy equal to 0 plus lambda into 0, which is 0, finally 0. So dfxy equal to 0. So at stationary value dfxy equal to 0, and also dfxy equal to 0 equal to d psi square xy, total differentiation of psi square xy is also del psi square del x, that is partial derivative of psi square with respect to x into dx plus d del psi square partial differentiation of psi square with respect to y dy. This is the total differentiation of d psi, total differentiation of psi square xy, that is d psi square xy is equal to this, plus similarly lambda into total differentiation of phi xy is also written as in the same way, del phi del x dx, del phi del y dy. This is here also these are functions of xy, these are function of xy, these are function of xy. This is. Now if we rearrange these terms, we get del psi square xy del x plus lambda del phi del x xy dx plus del psi square xy del y plus lambda del phi xy del y dy. This is equal to 0. This is equal to 0. We have chosen lambda. Lambda is the Lagrange multiplier. We have chosen lambda in such a way that these coefficients of del dx and dy vanish. We have chosen in such a way, we have chosen lambda in such a way that the coefficient of dx and dy simultaneously vanish, that is simultaneously they are 0. We have chosen lambda such that del psi square xy lambda del phi xy over del x equal to 0, equal to del psi square xy over del y plus lambda del phi xy del y equal to 0. These are equal to 0. We have chosen lambda in such a way that coefficient of dx and dy are separately 0. Coefficient of dx and dy are simultaneously 0. This is the rule of method of this is the rule of Lagrange multiplier. This is the method of Lagrange multiplier by which we are going to solve. We are going to derive the maximum value of psi square xy, that is psi xy. This is the method of Lagrange multiplier by which we are going to derive the maximum value of psi square xy and obviously maximum value of psi xy. Here this is the condition, this is the rule of Lagrange multiplier. We have already chosen the method of Lagrange multiplier to maximize the function psi square xy and also to maximize the function psi xy. We have already chosen this method, which is known as method of Lagrange multiplier. Here we have got these two equations, that is this equal to 0 and this equal to 0. So from this equation, that is del psi square xy over del x plus lambda del phi xy over del x equal to 0. This implies here also psi square xy is x minus 2 whole square plus y minus 2 whole square. This is psi square xy, and psi xy is also root over of square root of x minus 2 whole square plus y minus 2 whole square. Now this equation implies del psi square xy del x. If we differentiate partially psi square xy with respect to x, we get also by simplification we get x square plus y square minus 4x minus 4y plus 8. If we partially differentiate psi square xy with respect to x, we get 2x plus lambda into here also phi xy, that is constant function is also x square plus y square minus x minus y. So partial differentiation of constant function with respect to x is also 2x minus 1. Here also partial differentiation of psi square xy with respect to x. Psi square xy with respect to s is 2x minus 4. This is. So here x equal to 4 plus lambda over 2 plus 2 lambda. We have got the value of x in terms of lambda, which is 4 plus lambda over 2 plus 2 lambda from this equation. That is, this equation is 0. This is the equation. This is equal to 0. So this is equal to 0, and from this equation we have got the value of x in terms of lambda, which is 4 plus lambda over 2 plus 2 lambda. And also from this equation, that is del psi square xy over del y plus lambda del phi del x equal to 0. This also implies differentiation of psi square, a partial differentiation of psi square xy with respect to y is also similarly we get 2y minus 4 plus lambda into partial differentiation of phi with respect to y, here with respect to y, not x, we also get 2y minus 1 in the similar manner. So here also we shall get the value of x y equal to 4 plus lambda 2 plus 2 lambda. These two values are the same value, that is x equal to y. So we have got the value of xy as the same value, that is x equal to y equal to 4 plus lambda over 2 plus 2 lambda. This is x equal to y. Now if we put x equal to y in this equation, that is equal to 0, if we put x equal to y in x square plus y square minus x minus y equal to 0, we get x square plus x square minus x equal to 0, that is 2x square minus 2x equal to 0, which implies x into x minus 1 equal to 0, that is x equal to 0 and x equal to 1. X equal to 0 and x equal to 1. So as x equal to y, so for x equal to 0 we get also y equal to 0. As x equal to y, so this implies if x equal to 0, then also y equal to 0. So 0 equal to y, that is y equal to 0, and if x equal to 1, then also 1 equal to y, that is y equal to 0 and also y equal to 1. So there are two stationary points we have got. There are two stationary points. So there are two stationary points which are 0, 0 and 1, 1. This for the confirmation of maximum value. Now for the confirmation of maximum value, we have to check the sign of double derivative, that is double differentiation of f x y. We have to check the sign of double differentiation, total differentiation of f. If the sign of d2f x y is negative at any value of these 2 points, two stationary points, then this is the function is maximized at this point. If the sign of d2f x y at any points among these two stationary points is negative, then at this point the function is maximum. That function is maximum. So we have to check the signs of d2f x y. d2f x y. We have got df x y equal to del psi square x y del x plus lambda del phi x y del x dx plus del psi square x y over del y plus lambda del phi x y del y dy. We have got this relation, that is total differentiation of the function capital F x y. Now here also we have got del psi square x y del x is 2x minus 4 plus lambda into 2x minus 1 dx plus 2y minus 4 dy 2y minus 4 plus lambda into 2y minus 1 dy. This is df xy. This is df xy. Again we take differentiation on total differentiation of df xy, that is d2f xy. d2f xy is also 2 plus 2 lambda dx square plus 0. If we take partial differentiation with respect to y, this partial differentiation with respect to y of this function is 0, because this is the function of x. So partial differentiation of this function with respect to y is 0. So 0 into dx dy plus here we get also 2 plus 2 lambda dy square. Again, if we take differentiation of this function, partial differentiation of this function with respect to y, with respect to x, this is 0 because this is the function of y. So its partial differentiation with respect to x is 0. So 0 into dx dy, this is. So we have got 2 into 1 plus lambda dx square plus 2 into 1 plus lambda dy square, dy square. Now if we put xy as 0 0, that is we have if we shall take the point 0 0 if we put the point 0 0, that is x equal to 0, y equal to 0 in this relation, we get that is 0 0 equal to 2 1 plus lambda. Here also x equal to, we have got 4 plus lambda 2 plus 2 lambda. So if we put x equal to 0, we have 4 plus lambda over 2 plus 2 lambda, that is 4 plus lambda equal to 0, that is lambda equal to minus 4, lambda equal to minus 4. So here we can put lambda equal to minus 4 dx square, and also 2 into 1 minus 4 dy square, which is negative, So d square fxy at 0 0 is negative. So at 0 0 the function is maximized, that is psi square xy is maximized. So at 0 0, so at 0 0 psi square xy is maximized. Now we take the second point, that is 1 1, for verification of the sign of d2fxy. Also we can take the point d2fxy. If we take the point 1 1 for verification of the sign of d2fxy, we also get 2 into 1 plus lambda. Here if x equal to 1, if x equal to, here x equal to 0 is chosen, if x equal to 1 is chosen, so 4 plus lambda over 2 plus 2 lambda, that is lambda equal to 2, lambda equal to 2. So here lambda equal to 2 dx square plus 2 into 1 plus 2 dy square, which is greater than 0. So at the point 1 1 psi square xy is minimized. So at 1 1 psi square xy is minimized. So maximum value the max so the maximum value of psi square xy at 0 0 equal to 0 minus 2 whole square plus 0 minus 2 whole square, that is 8. So psi xy max is also a root over of 8, that is 2 root 2, because if psi square xy is maximized, then also psi xy is maximized, because psi xy is non-negative. Value of psi xy is non-negative, that is always greater or equal to 0. So if psi square xy is maximized at any point, then at that point also psi xy is maximized. So psi xy is also maximized at 0 0, and the maximum value of psi xy is 2 root 2. Psi xy means the maximum value of modulus z minus 2 plus 2y max equal to 2 root 2. This is the maximum value of our objective function modulus z minus 2 plus 2y.